Hi class, welcome to our first lecture on the chapter 6 of quantum mechanics. And again, our main reference here is Introduction to Quantum Mechanics by David J. Griffiths, and I recommend this book for you. And I also have to point it out that you may not watch this lecture continuously. You can do it by parts. Don't do it in one sitting, because it's you may have difficulty in mentally digesting the contents. So to start with, this chapter, by the way, is time-independent perturbation theory, and we start with non-degenerate perturbation theory. So now consider a system, say for example the one-dimensional infinite square well. We know the Hamiltonian of that infinite square well, and we also know the energies of that infinite square well. They are just given by the Schrödinger equation here, or time-independent Schrödinger equation. And we have also solved for the complete set of orthogonal eigenfunctions. So when you get the inner product of the two wave function, it just will give you the Kronecker delta here. And of course, for the Hamiltonian H of O, that's the original Hamiltonian without perturbation, meaning without any disturbance at all, it gives the different energies En of the system. The different energies En, you have a subscript O there for being the untouched energy. Now, if the potential is disturbed or perturbed slightly by putting a little lump on the bottom of the well, what will happen to the energy? So this is now your infinite square well. It has a lump at the bottom. This one here. So how is it to solve for the new eigenfunctions and eigenvalues? Because definitely the energies, or the energy of the system, will have to be altered because of this perturbation, and also because we have altered the Hamiltonian initially, and precisely we have altered the Hamiltonian. So for the new Hamiltonian, the energies will be given by this. Now, this lump will make it difficult for us to solve the Schrödinger equation exactly. So we will have to find new ways to approximate the new energies. So we use perturbation theory. This is a systematic procedure for obtaining approximate solutions to the perturbed problem by building on known exact solutions to the unperturbed case. That's why the superscript O there is what we call the original unperturbed Hamiltonian and energies. So we begin with writing the Hamiltonian as the sum of two terms here, the original and the perturbation, where the lambda here is just a constant. It's just an intensity of the perturbation. So we can take lambda to be a very small number. That means we're just perturbing the original potential very slightly, or very minutely. And then we can take lambda to be 1 later on, and so that we will be again we consider very small numbers, so that our Hamiltonian will not be disturbed, abruptly. So in this case, we can write our wave function and the energy as powers of alpha. So here we have this one here, and so the first order correction would be this one, because these are the original energies and wave function. This is the first order. This one we kind of ignore this one, because lambda square is already very small, super small, because lambda is already very small. And so again, en 1 is the first order correction to the nth eigenvalue of, or the energy eigenvalue, and phi n1 is the first order correction to the nth eigenfunction, or the wave function. And the second order would be this one here. So we go back to 6.3, since we have already expanded our Hamiltonian and energies in terms of lambda. We can plug in our expansion to here. We can plug in our expansion to this equation, and again we ignore higher corrections. We just get the first order correction, because we're dealing with very small lambda, and it would just be a good approximation if we consider lambda, the first order correction. It's still a good approximation. However, when we do the second order, then our answers would be more precise in that case. But the first order correction we have to master first before going to the second order. So we substitute phi n to the equation that we've shown before. So this is so we take note of these equations, this one and this one here. We plug those to 6.3 here. Plug it here. So now what happens, you can actually follow the process. You can write the process on your notes and follow and be able to get the result as well. So by plugging, we will arrive at this on the left side, and this is on the right side. Now we collect the powers of lambda such that we have this one on the right side, I mean on the left side, and this one on the right side. These are just the original Schrödinger equation, but here is now the correction. So we can discard this and just look at this one here. We can just look at this term. Anyway, I will just erase this. So we just look at this term. These are the first order correction. So this is the first order correction, and this is the second order. And you can also do higher orders, but of course your lambda is very small, so higher order correction would be I mean, it doesn't really affect much. However, we're just concentrating on the first order correction at this time. So now we go to the first order perturbation theory. So take the inner product of equation 6.7, we go back to it, with phi n0, the original wave function. By the way, this is this one here, that could also be written as phi n0 h0 phi n, but it could also be that this is not present, so that's just the same. It means the same, this one. So anyway, when you see that in other books, don't get shocked, it's just the same. So we take the inner product of 6.7 by phi n0, and then, by the way, as you know, this one, when you have like A, inner product of A, that B, this is actually equal to A star B. This means this is a conjugate of A. And when you have an inner product, this is just, so if you have two functions, for example, so if you have two functions f and g, this is just f star g, d some variable dx, say for example. So here this is actually phi n0 star, this one. So we get the inner products of them. We have, of course, our Hamiltonian, our original Hamiltonian is a Hermitian. So we can put it outside, or we can actually just put it anywhere inside the inner product, so that you can transfer here without getting the conjugate, because it's a Hermitian, the conjugate is just the same as the original. So you have this, and then of course this one here, this thing here, is equal to this, but En of O is a constant, so you will have this one. And as you can see also that when you get the inner product of two normalized eigenfunctions, the inner product would just be a Kronecker delta. If you're n, if you have a different subscript, you have a Kronecker delta. But if you have the same subscript, well, of course, Kronecker delta will turn to 1. So this is just 1. So that this is just equal to 1. And your energy correction then would be, the energy correction here would be this. By the way, first things first, this one here is just equal to this one, so that your E1 would be just equal to that. So we now have so let me just erase this one and emphasize the result, which is this one here. This is a very important result. That's the first order perturbation theory. It's also a very important equation in quantum mechanics. So I can also write this as, yeah, this is just when the bar is not written or is not placed there. So anyway, that's the first order correction. So we have to remember this. So the first order correction to the energy is the expectation value of the perturbation in the unperturbed state. So we now take an example. The unperturbed wave function of the infinite square well is given by this. We have arrived at this result before. Suppose that the perturbation of the system is by simply raising the floor of the well by a constant amount V sub O. So H prime equals V sub O, and the first order correction to the energy of the end state is this one. So the first correction would just be V sub O. So if we go back, this is just the formula, and our H prime there is just V sub O. So but V sub O is a constant, so you can just take that out of the inner product, and the correction then is just this V sub O. So now the corrected energy levels are then En equals En O plus V sub O. So you're just lifting the energies by an amount V sub O. In the case the first order theory yields the exact answer, evidently for a constant perturbation, all the higher corrections will vanish. That's for only for a constant perturbation. So how about a constant perturbation over half the well? So if the perturbation is only here, not the whole thing, so what will be the energy or the corrections to the energy? So again, using this formula here, sorry for that, using this formula here to get the first order correction, we have to take note of this wave function, which is this one, and so we'll be able to get this one here. This is just equal to inner product of phi n sub o v sub o over 2 phi sub o n. I'm sorry, this is not v sub o over 2 but just v sub o. But again, in this case, you have to integrate only from 0 to a over 2, because the perturbation is only from here to here. If the perturbation is from here to this one, then the limit would be from a over 2 to a. And of course that will give you a different result, or maybe the same, but because of that limit you will probably have a different result. But maybe it could be the same because the range is the same. But yeah, you can solve it also later. So this is not the exact result, but it is reasonable in the first order approximation. Now, to find the first order correction to the wave function, we now use equation 6.9, and we will go back to that equation. Here, and let's take a look at this equation. So this is of course the first order energy correction. We use this result. However, we have to look at 6.7 first. So here we have, this is okay, this is okay, this is of course a perturbation, this is okay. This one is okay, this one is okay, we have that value, and this one is also okay. So we can now factor out phi 1 so that we will have this. Here, the right side of the equation is a known function. So this is just an inhomogeneous differential equation of phi n 1. So we're looking for this. Now the unperturbed wave function constitutes a complete set, so we can write any function, and as a matter of fact, phi n1 to be an expansion of that complete set. So we can write phi n1 like that. We don't include m equals n anymore because of course, if phi n1 satisfies this equation, this one, then of course this will also satisfy that. So we can, from here we can do something to find CMN, this one, by putting this equation here to 6.10, which is just this one here. So doing that, we will be able to arrive at this equation here. So again, taking the inner product with phi 1 sub o, both sides, we have this on the right side and we have this on the left side. So only when L is equal to n, the left side would be 0, and then we recover 6.9. But if n is not equal to n, then we would have this. Sorry, we're getting the inner product with phi L0, not phi 1 0. So now, when, of course, if L is equal to n, then we have here for this one, for this part of the equation, that would be phi n0, phi m0, and this is always 0 because m is not equal to m. I mean, n is not equal to m, as we have set here. Not m is not equal to n. So everything on the left side would be 0, and so if L is not equal to m, or L is not equal to n, then we will have Cm to be this one. And our phi 1 will now be this one here. So the denominator here is okay. It cannot be 0 because m is not equal to n. And this is important result because we have the unperturbed energy spectrum here is non-degenerate. But how about if the unperturbed system has a degenerate energy? So how would we do that? So this is actually your wave function correction. So you can start with for n equals 1, then you can just put 1 here, 1 also here, and then you can start with m equals 1, 2, 3, and so on. So that is the correction to the wave function. Now, if two different unperturbed states share the same energy, there will be a zero denominator that will cause problem. In this case, we have to use degenerate perturbation theory. So we now know the correction to the wave function. So here there's a warning. Whereas perturbation theory often yields surprisingly accurate energies, but the wave functions are notoriously poor. We can measure experimentally the energies to be really close to the exact value of the perturbed system, but the wave functions will be really would have some problem. I mean, that's well, some work have to be done to close in with the correct wave function. Now let's do the degenerate perturbation theory. But you could also do these problems in your free time. So here's a perturbation, one of the perturbations that are important to study. And you can also do the harmonic oscillator here. So anyway, those are some problems that you can do in your free time. And I know that you have a lot of free time. So now, before we go into the degenerate perturbation theory, we will now tackle the second order energies, second order correction to the energies. So we had En1 for the first order correction. We will have now En2. So anyway, En2, we can go back in the earlier slides, and I'm sure that's on your notes as well. You can look for that quickly and do some algebra to be able to get this one here. This is our En2. In this case, there's a presence of En1 here. So we will have to know exactly what En1 first before we can know exactly En2. So it's important to also know, I mean, it's important not to forget the previous results that we did. However, you have here two normalized wave function, different orders, so this would have to be 0. So now En2 would be this one. Now it's only one term, but we can expand phi 1n in terms of phi m0, so that we will have this, and Cmn is also this one, as we have previously derived. So therefore what we have now is this one, the correction, the energy correction of the second order perturbation. So this is the result for the second order energy correction for the perturbation theory. But you can also proceed to the third order, fourth order, but well, those are very negligible already, but you can do that. So these are the problems that you can solve for this one. And now let's go to the non-degenerate perturbation theory. I mean degenerate perturbation theory. The first that we discussed was non-degenerate. Now we'll go to degenerate perturbation theory. One in which some energies are the same. So if the unperturbed states are degenerate, that is, if at least two distinct states, phi A0 and phi B0 are the same, have the same energy, then ordinary perturbation theory will not work. So equation 6.12 will have a denominator of 0, and it blows up when you do this. So let's proceed with that. So in this case, you will have to write the wave function to be a linear combination of the states of the same energy, and you have to do this. So these ones, the phi A0 and the phi B0 are states with the same energy. So in order to make them to include them all, we have to find or write a wave function that's a linear combination of the states with the same energy, and in this case we only have two, so we can write firstly this one. So here we have this combination is also an eigenstate of HO, with the same energy here. Typically, the perturbation will break the degeneracy. So if you disturb the potential a little bit, the degeneracy will break. So if you have an energy here, two wave functions with the same energy, so when you do the correction, one of the wave function will have this energy and the other one will have that energy, so they will break. They will split into two. The essential problem here is when the perturbation is turned off, the upper state reduces down to one linear combination of phi A 0 and phi B 0, and the lower state reduces to some other linear combination, but this good linear combination will not be known beforehand. So in this case, the alpha and beta will have to be adjustable. We have to adjust this one because you have a linear combination of these two, where the contributions of phi A would be, phi A0 would be alpha, and the contribution of phi B0 would be beta. The first order energy cannot be calculated because the unperturbed states to use is not known. So again, we consider the Schrödinger equation, where H here is the perturbed Hamiltonian, and of course you expand again the energy and the wave function, and then collect like powers of lambda, the same as what was done in the first order correction. So now you have this one. By the way, of course, that is this is trivial. So by the way, this 6.19 would have to be substituted to 6.18 here, so that you can get the correction. So you collect like exponents, like powers of lambda. So now you have this one here. So we will now get the inner product with respect to phi A0, and then later on we will get the inner product with phi B0, since there are two of them. So we will have this, again the first the Hamiltonian H0 is Hermitian, so the first term cancels, so this will cancel, and you will only have this. Here you have separated phi sub O is as equal to lambda phi A0 plus beta phi B0, so that they appear here. So we call this we recast this as this one, where the W's are defined in this way. So it's a completely different way of doing the corrections for the degenerate case. So for B, if you do the same thing, you will also get this one. So the W's are known and are the matrix elements of H prime with respect to the unperturbed wave functions phi A 0 and phi B 0. And now multiplying equation 6.23 by WAB and using 6.21 to eliminate beta AB, 6.21 is here, we will have now a quadratic equation for E1, and our E1 will just, so this will now, we will now arrive at this. You can do the details on your notes, and this is now the quadratic equation of E1. Of course, we're going to find E1 in terms of the W's, but of course the W's here, the W's would just be this one here. So this is just an inner product, although you have to do the integral later on in the example. So now you have two roots for the corrections, the energy first order corrections for degenerate case, for the degenerate perturbation theory. So one is E plus and the other one is E minus 1, and they just differ here. So now if alpha is 0, then beta would be equal to 1 and WAB would be 0, and E1 will just be given by WBB. Or you can also do the case for alpha equals 1 and beta equals 0, and the energy correction there would just be with respect to WAA. So we will have E plus to the 1 would be equal to WAA, which is this, and E minus 1, E minus to the 1 will just be this one. Those are precisely what are obtained using the non-degenerate perturbation theory. So in this case, we're lucky that the states, or the linear combination that we did, is already the correct combination, but the linear combination would be something else. However, that was the linear combination that worked initially. Now we'll go to a theorem. Let A be a Hermitian operator that commutes with H prime. If phi A0 and phi B0 are eigenfunctions of A with distinct eigenvalues, that means different energies, here, distinct eigenvalues, so that those have different energies, then WAB would be 0, and hence phi A0 and phi B0 are good states to use in perturbation theory. So here you can show that using this as a proof. So since they commute, A and H prime commute, this is equal to 0, the commutation is equal to 0, and you can do this. So if they are not equal, then if they are not equal, then the only way is that WAB is 0. So that's how you prove that. So in that case, so anyway, this is just mathematical. What's important is the results that we have achieved, as in equation 6.26, this one. So if you have so much time, I know you have, you can solve problem 6.6 and also problem 6.7. So higher order degeneracy would also take some time, so we will discuss this in the next session. So I hope you've learned something in this particular part of the series, and hopefully the higher order degeneracy will be discussed in the next lecture, the next series, the next of the series, I mean. So be able to do the summary and rewrite the examples that I've discussed for your Google form assessment.